Welcome, everybody. This is after the break. This is a tough part for you to stay awakened. After talking this morning about the new C++ standard and its core features, I want to talk this afternoon about the new library features we have in C++ 17. Again, for those who are just joining and didn't hear the first talk this morning, my name is Nicolai Josuttis. I'm self-employed. I'm part of the standardization committee for 20 years now. And so partially it's all my fault, but partially it's your fault if you don't like anything. You were not there. We are community-driven, and everybody who's there has influence. So I will usually say that's your fault, not my fault, if you ask for something. And yeah, maybe that's it for the moment. Most interesting things I want to tell you. So we talk again about C++ 17. As said before, we have a 3-year schedule right now to come out with new C++ versions. After C++ 11 was a big improvement and gained a lot of momentum, we now have C++ 14, which had only some minor extensions, and now, after expecting more, we have C++ 17, which I would categorize as a medium improvement, and the next improvement is already there. We are already working on C++ 20, which will hopefully and probably be, again, a major improvement. It might be even become bigger than C++ 11 because it will really change the way people program in C++. And again, the hint that there is already support for C++ 17. We have support in GCC and C++, especially in version 7.1, which came out some weeks ago. And Clang 4 also supports it. And then we also have Visual Studio 17, which also supports some of the features and will have updates also this year. So at the end of this year, I expect that you will find on all major platforms more or less support for C++ 17, maybe not completely, but for the main cases. So here we talk about the library. And the library means, of course, new data types, but not data types which are fundamental data types. Data types we define in the standard library as an application of the language. And the funny thing is that the library in C++ always, or pretty often, extends core features which we, for some reason, think should not become core features but library features, although you could argue that they should be core features. So some of these basic data types we also started to standardize in C++ 17. So the first thing is string view. We have now a new string class. So after std string, which owns the memory for the data it holds, either by allocating memory on the heap, or maybe for short strings with some optimization implementations use their own memory they have on the stack. Now we have a data type representing strings, but not owning the memory they refer to, which is, of course, a dangerous thing. To some extent, this is a string reference, but with an API of a string. And it should be cheap to copy, but as I said, pretty dangerous. But there are enough application of that. For example, I was working at a company which created a new database which should deal with big data. So you couldn't keep all the data in memory, so you had to keep it on a file system. And what you usually do is then you map just the file system into your database with mmap calls or something like that, and then instead, it would be far too expensive to copy all the strings in the map, just refer to them and use them as strings. That means that string views have not all guarantees normal strings have. The most important guarantee which is missing is the string does not necessarily end with null termination, so with a null terminator, because here you see on the right side we refer to data in some memory, and after data there might not be a 0 or \0 character. It could be, but then it's organized that way by those who provide the data for the string. And it might also happen that such a string suddenly has a value which is null pointer, which is nothing, referring to nothing. That's also different from traditional strings. Traditional strings don't have this state. They have then, if you don't pass anything for initialization, they represent an empty string, which is a different thing. So that means always use size and check the size before you access elements or the data or pass the data around. There is some support, but not support in every direction regarding string view. It came in pretty late for C++17, so we have something like string view for different character types, but we, for example, have no support for the interface, regex interface, to also deal with string views. And we have a literal now allowing easily to create a string view just by adding the suffix sv after a string literal. String views are cheaper than strings, and a pretty easy example is if you declare a function to take a string, a traditional string, or traditional in the sense of C++, and so an std string, and now if we now declare something to take a string view, it becomes cheaper to pass a string literal, because in the first version you have to allocate memory for the string holding the data, and in the second version, taking a string view, you have no allocation at all. You only have to compute the length of the string. So that makes passing string literal cheap. And that in general raises the question, are string views the better string API? So what should we do with existing code? Should we expect to have a string, or should we expect to have a string view? And the answer is, it depends. The point is, if you, for example, pass your string to a C function expecting a null at the end, then you anyway need an std string, so it's probably not worth it to change it. But there are other examples. For example, here you see an example where we have toString method taking a prefix and a time point, and a time point is part of the C++11 library to compute times, and there's a conversion function taking this time point, converting it to a time t, and then with ctime converting it to a visible string. And then, because this string contains a new line at the end, when you call it created with ctime, then we remove the new line, and then we return the prefix plus the string. If you take this traditional code, traditional since C++11, then you can think about taking a string view, because you don't need a 0 terminator at the incoming string. And note, by the way, that string views are usually passed by value, not by reference, because it's cheap to pass them. And we can even inside take ctime takes a string view, which also saves some memory, because the ctime value is available until the next time ctime is called, which, by the way, is not concurrent safe, so thread safe, but it's anyway not thread safe to call ctime. so it's a little bit less thread safe than before. So in commercial code with multiple threads, you anyway needed mutexes here. And then there's the string view is a read-only string, but by definition you can change the size. Well, you can reduce the size. You cannot extend it, but you can reduce it. And therefore, there are some methods saying, I want to skip the last character or the first character, because then we just refer to a different location, to a substring of the string we had before, which we do here. So there are some ways now to change your APIs to the modern style, but beware, we are ourselves still trying to find out what exactly the guidelines is to switch to string view. As said, it's a cheaper API, but it has some constraints, so be careful to use it in general. We will find out over the next years. Then we have some data types in the standard already, which more or less count as core database, core data types, like pair, for example. And we have now a few other more or less core types which are able to hold a value. And if you see the terms and you know boost, you might know them already, but beware, they are slightly or significant different. So they have the same idea, but beware a little bit. So we have optional, variant, and any, and all of them solve a specific problem you might have if you deal with values in general. So the first problem, so for the first solution is optional, and optional is just resolving the problem that you might have a value of a certain type, but you might also have no value of that type, which is different from a special value. So that, for example, for std string, beside the empty string, you also have no string, which means semantically you give this value type a reference API. And that's optional of int, and here's the example that explains how to do that. Optional just takes a type it represents, and it adds an additional state you can set and you can check. So here, for example, we take a string and we try to convert the string to an integer, but if the string is not convertible to an integer, s2i throws an exception, and in that case we return a null opt, and a null opt is saying, well, I don't have a string, I don't have an integer here, so we return either the integer or no integer at all, and which means we don't have to take one special value like -1 as the value representing no integer, which is usually a bad interface. So here's the loop then taking and calling this as int function for different values, and here you see how you test it. If it converts to true, then you have a value of that type and you can access it by the star operator. Otherwise, you can do whatever you want if you have no type. Helpful in a couple of places. This is pretty, by the way, this is pretty near to the existing boost interface of boost optional. Then we have a second type taking, which is a variant. A variant is a kind of a union. So that means an object that can have multiple types. It's a finite amount of types it can take. When you declare a variant, you declare what kind of types the object might take. And if you know C and C++, then we have this language keyword union, which allows to say I can use my bytes in my object as an integer or as a character array, and some people even use that to convert integers to byte sequences. This is not the same. This is different in a way that there is no different interpretation of the bytes it has. This object knows which type it has and only allows to deal with the type it currently holds. So either the object holds an integer or it holds a string, but if it holds a string, you can't ask for the integer value of this object. That will result in a runtime exception. So this object knows what it holds and is type safe, but it only needs memory for the maximum of the size of int and the size of string. That's a big advantage it has. So we have here a variable taking being either an int or an std string. It is initialized by 42, so that means that the compiler can find out, because 42 is an int, that it's initialized as an int. but later on we can assign a string or something that converts to string, which of course has to be not non-ambiguous. So if there are two types where a string literal could convert to, this would not compile. And then we can access the data. With get, you can access the data knowing the type, and then you have to pass the type. Alternatively, you can pass the index, so the type interpretation you want to have. So because if you say get 0, you get the first type, which is an integer. And if this is detectable at compile time, that there's an error. So if you pass an unknown type, or if you pass an unknown index, that's a compile time error. But if you don't know what it holds currently and both is valid, this might result in a runtime error. So an exception. A couple of interesting things here. The first thing is this allows to hold a type several times. That means semantically we can hold two different integers. One integer representing some semantics and some integer representing other semantics. So if you have different situations, you want to represent different situations, the first int might have 42, and the second int might have 42, but they might represent different situations, different states. And of course, then it's not possible to say, I want to get the int, because that's ambiguous. Then you have to use the index to clearly say which int you want to have. Everything else is as before. And if you know boost and boost variant, there is a significant difference. In boost variant, such a variant can become empty. And because it can become empty, you need heap allocation, heap memory, to be exception safe. And this drawback was fixed, or was this rediscussed when we standardized variant for C++17. So now we have a situation where we say this type does no longer need heap memory. So it simply allocates, again, the maximum of the possible types. As said before, in boost, you also could do that, but to keep a copy of your current data, if an exception throws, then the data type still needed heap memory, and that's gone now. But the price is that you might come in an interesting state. The state is, I'm not really empty, more or less, I don't hold a valid state because an exception happened during setting a new value with a new type. And that's a very rare case that can happen, but it can happen. So we have no member function calling type. The member function is called valueless by exception. And you create it by doing something like this. You see here, I have a variant taking a float or an int, and I have it currently has a float, and I place inside the variant an int, but with a conversion to an int. So I change the value, but while I assign the integer, this conversion throws an exception. And then this object is in this strange state, which usually is anyway a state where you would not use the object, but if you ask the object, you have this strange state, valueless by exception. And as said again, the goal, the benefit we have, we don't need heap allocation for this type, and that makes it pretty cheap compared to boost variant. And there's a visitor interface. If you have different types, and it's tedious to check for which type it holds, and then have different functions called, there's a general way to provide an operator, a function call operator for each and every type, and then you can simply pass this visitor to a variant, and that means if it currently holds a double, it calls the first function. If it holds an integer, it calls the second function, etc., which might also be generic template code or lambda or something like that. So it can be pretty flexible. Okay, the third type we have is any. Any is also a new way to hold a type, a value, The first thing was to make the value optional. The second was that the value might have different but a finite number of types. And now we have a type saying my value might be any type at all. I have no limits. It can be any type, even a type not known when I compile this code. Well, when I use that template in a header file, it is compiled when the types are clear, which are used. And this is the trick here is that any takes the value and remembers the type of the value. So if I assign 42, it remembers inside the type ID of 42, which is an int type ID. If I later assign a string, it remembers the type ID of a string, etc. So it simply stores the type ID of what was assigned there. And then later, when you want to access the object, you can only access it if you double check that the type ID is wrong, or you might get undefined behavior. So here you see some examples. I can ask, do I have a value? So this type can be empty, or the values of this type can be empty. And then I can ask, is the current type a string, an std string? So does the type has a type ID of a string? And then I can anycast, so cast it to the corresponding type and use it. And as said, this will work with any type, even with types that later come from any other source or any other library you have. So, but of course, this, because you don't know how big data might grow, this needs heap memory to allocate corresponding storage here. A feature we have here is you can have move semantics with the anytype, which was not supported yet in Boost with the anytype, I think, as far as I know, but I might be wrong here. So we have some semantics from them. I recently tried to compile it. It didn't work. This code didn't work, so I have to double check it. So there's a question mark on this slide currently. Yeah, and we have a fourth basic data type, which is a totally different type. This is a type called std byte, and it's representing a byte. By definition, a byte has a size of 1. So that means it has a size of character. So that means that it's open how many bits it has. It depends on the platform. There are platforms that have 64 bits, so whereas a character has a size of 64 bits, so a size of 8. And on that platform, the byte would also be 8. A size would also be 64 bits, have 64 bits. So the idea here is, and there was a lot of fight when we standardized it, the idea that got the interface was to say a byte is not an integral data type. So you can use it as an integral data type, but it isn't. It's just a byte. And that means we have operations like bit operations, like left shift, right shift, exclusive or etc. So all the bit operations, but we don't have plus or minus or something like that. So this should not be yet another character type or something like that. And the idea is to make clear, if you use it in your program, that you don't use here this type as a very small integral value, but you use it as a byte, as a representation of 8 bits usually. So that's the design of the API and in the interface. Note that the definition of byte is just an enum. So we have extended the language that now we can initialize such an enum with curly braces, which was not possible before with some conditions. But any other initialization is not possible. And there is no implicit conversion to bool. So you can't test whether the byte is true. Yeah, a byte is not an integral type. It's also not a Boolean type. It's just representing bits. So you have to convert it to the corresponding idea, or you can have to compare it with a byte with full of zeros. So that's possible. So there is a a function to integer for bool, and then to integer you pass the type you want to convert this, the integral type you want to convert this byte to. And that way you can use this in an integer expression, or you can assign it to any integer or some other types. Okay. That's the fundamental data types we have. What else do we have? We have a really new library. It's called the file system library. The file system library comes from Boost also. Also, it has some modifications. So the idea of a file system library is to be able to portable program with file systems. It's not creating files, we have that already, but it's more something like creating a directory, iterating over a directory, recursively go through a directory, find out whether a path is a root, something like that. So all these file system operations. I think the best example is if you just see code and you see here the general idea. If you include file system, then you have the data type file system path, which represents a path in your file system. You can check whether this exists, so whether there is something, and if this something exists, you can double check about is it a regular file, and you can ask for its size. Is it a directory? Then you can use the directory iterator to iterate over this directory, and you can do other things, a couple of other things, including printing out the path. This more or less is no change to Boost. I just had to change the namespace from Boost to std and the include statement, and it did recompile. Here's another example which shows a little bit that you can create things. So you can create a directory, you can create a symbolic link, you can concatenate paths with a slash operator or slash equal. Yeah, things like that are supported. The specification says that in case there is no equivalent operating system support, for example, if your operating system does not have symbolic links, you have to do two things as somebody providing this library on your platform. You have to document what happens instead, and you have to be as close as possible. So if there's no symbolic link, you have to double check on your platform what this call means. And just to ensure in Windows we have symbolic links. Some people don't know that. Again, no change in API. We try to abstract operating system. That's a nightmare, I can tell you. I learned so much. I had learned a lot about symbolic links and where am I when I traverse through symbolic links. It's really a nightmare. And so we abstract some things. So we say a path can have a root name, can have a root directory, a directory separator, and then a file name. And the file name can exist of a stem and its extension. So stem is the part without the extension. And then we have tried to map this on different operating systems. So here is another example, and you see how it behaves under Unix and Windows. We have a path declared there in the middle, foo_bar data.txt, and then if we print it out, we have the general format, the general POSIX format, but if we make it preferred as a preferred syntax of the operating system, you see that on Windows the slashes are replaced by backslashes. And then we have again APIs to get a lot of information about this path. Look at the last line here. If we ask, is this an absolute path or not? It depends on the operating system. Because in Unix, this is an absolute path, because we always start with root. But in Windows, we have the drive, so C:, or something like that. So in Windows, this is not an absolute path. So we are not standardizing more than we can. So there will be differences, and you have to deal with the differences if you deal with the different operating systems. as said, this is a library we had in Boost, but we made some changes. And sorry, I disabled showing those user slides I wanted to show now, so I have to enable them again. Where is it there? Just give me a moment. So I give you some examples what changed. For example, in Boost, we have defined that an extension always starts with the last dot. So if you have a file called .git, and you ask about the attributes of this file, the answer is this file has only the extension and no file name, no raw file name, which we call a stem, which we think is not valid. I mean, .git is there, it has a dot to not be visible by default, but it's not a file without a name and with the extension .git. So that's not the right semantics, we think, but you can see different solutions for these problems in different file system libraries in different languages. So we changed that behavior, for example, and we changed a couple of other minor things there. Yeah, I think I said that already. And that has consequences. Just this little tweak might change something. I guess there was another thing saying that if you have foo bar / dot, it was more or less the same as foo bar /. So it's right in the middle there of the slide. And foo bar / without a following file name was implicitly converted into foo bar / dot. So if you asked, is there a file name? Yes, there was a file name, and the file name was dot, which we also changed now. And so we said, no, there's a difference, and we have different behavior if there's a dot after the path separator or not. That will change the APIs a little bit. So if you convert from Boost to STD file system, please adopt your code. It will not behave exactly like before, and we decided not to change, not to provide a new API there or different API. So you will see that the code no longer compiles because it uses a different header file, but don't just change the header file and expect everything to work. And there's a third thing that drove us crazy like nuts. It's symbolic links. So look at the example here. You have here a path, and every red arrow is a symbolic link. So this refers to another location in your file system. And if you go to ADE, look at that where you are. ADE refers to AB. So if you go to the directory ADE, you are actually in AB. Now things get worse. If you have a Unix shell and asked where you are, the Unix shell will tell you you are in ADE. But that's a lie. That's a convenient function of your shell. You are not there. You can find it out if you ask pwd, so print working directory minus capital P, then you get the real place you are in. And if you go up with CD : in a shell, you are back in AD, but if physically you are really in AB, then you then : would move you to A. So we had to deal with these problems and to standardize here something. Yeah, so here are some rules. And why did we need that? Because we decided that we provide a function computing the relative path between two paths. And that become incredible crazy if you have to deal with these situations. So the outcome is we have a physical relative path and a lexical relative path. So a lexical relative path doesn't take the operating system into account. So not dealing with any symbolic links, but a relative path not lexically might consider symbolic links. So we have not just one API to compute relative path, we have multiple APIs to do that. And now you know why Boost didn't have a support for something like compute the relative path between files, because it was very tricky to do that. But we did, and that's a good news. So what else? Let me talk about some other libraries, some minor libraries. File system is certainly a big library and a very helpful library. The first thing I want to show you is that we parallelize the existing STL algorithms. So that means whenever you do something for each and every element in your container, for example, transforming it or computing, I don't know, the square of the elements, etc., you can now benefit from the fact that we have multiple CPUs or multiple cores, multiple threads available. So we have thread multi-parallel support for the implemented algorithm and for more or less every algorithm we have. Unfortunately, things become tricky sometimes then. So you have to be aware what is possible and what not. So we have to ask for some guarantees. For example, if we process with multiple threads 3 different elements of a vector, and the first step is to acquire a global lock, then you run into a big problem because the first thread gets a lock, and then the next thread is blocked, etc. So we have to deal with some ideas of which guarantees we give. And here you see a general trial to explain what we guarantee. We have different policies you can apply then to the algorithms. The first policy is sequential execution. That's the way things are handled now. You have one thread doing all the steps for the first element, then all the steps for the second element, and all the steps for the third element. So the steps would here A, B, C, for example. Parallel execution means that you can use multiple threads, but each thread is sequentially processing one element. So 3 different threads might take 3 different elements, but for each element, they, for example, in A, lock something, do something, and then unlock something. And the third thing is to say, well, we have even not a guarantee that the elements, if they are taken, are sequentially processed. So a thread might do the first step of the first element, which is A for the left part, then do the first step of another element, and if this step is taking a lock, then you have a problem, then you have a deadlock, then you're out of order. So you need some additional guarantees to be able to do that, but if it helps, it can be even better, which is usually called vectorization in big Cray machines, etc., where you say, well, we in parallel do with threads the first step of some computation of the elements, but you need some guarantees. So here's how you do that, how you deal with that. Each and every STL algorithm has now a new first argument, and here you select the policy. You say you are not allowed to use multiple threads. That's on the bottom. Execution sequentially. That's what we had before as only option. And the other 2 options I explained already. So parallel or parallel even not sequenced and no guarantees at all, which is usually fine if you only do local processing like here. But at the moment you have a lock guard used, which is shared among the different elements, you can't use the flexible policy on top here. When we did that, we added new STL algorithms because it turned out that we get some drawbacks or some things were missing. For example, accumulates the elements of a container, but we guarantee the order. And that's a big drawback when making this parallel, because then to keep the order, you have to compute the order of the results the different threads give you, and to deal with the order. So we introduce a new algorithm, reduce, which does no longer guarantee about the order the operation like plus or so is applied, which means that, for example, you can't do that for floating point values because different results might occur, but it's fine for adding integers, for example. It doesn't matter in which order they are added, or you compute the sum. And we have other examples like that where we, due to the parallelization, introduced some tweaks of the existing algorithms with a new name. We have 2 or 3 other things. So clamp is just combining a min and a max call to say I wanna constrain a value between the lowest value so-and-so and the highest value so-and-so. And we have sample. Sample is also interesting for people who do need random numbers or random subsets of sets. The idea is if you have a set, say, of 1 million values or 1 million customers or 1 million objects of certain data, and you need just random extraction from them. So, for example, 100 of them, but you want to have it randomly computed which 100 you extract from them. This is called sample. This interface does that using one of the standard predefined random number generators. And we also have new searchers, Boyer, Moore, and Horsespoon searchers. I have no clue about the details here in the fact what they are doing better than before. I'm not an expert in that area, but the whole idea is if you have a large string, so it's not like this example, it's if you really have a large string, say a complete book or even more, and you want to fast search substrings, then they internally create hash values, etc. And by this trick, which you can find if you search for these 3 names, that are 3 different names of authors of these algorithms, you can a lot faster find substrings in such a string. So for those people who do text processing of large strings, this is a significant improvement. A couple of other things. We fixed some gaps we had in some containers. Try and place was missing for maps, and place back and front was missing or is now returning something. We added data, a non-const data for strings, etc., etc. I think vectors and forwards lists now support incomplete types. By the way, you see on the right side a so-called paper number. Every proposal we have in C++ is driven by a paper, and these papers have different numbers. You can see that the scheme of the paper numbers changed over time. So in the past we had N numbers, now we have P numbers. If you look at the internet to these numbers, you will find the original paper saying what was the intention and what should change in the standard. So here's one example, which was a point here close to the end. We extended the interface of associative containers to make it cheap to move the elements into another container of the same category, I should say, or to modify it somehow. Here is an example that explains it. If you have a map of 3 elements, and each element has a key, 1, 2, 3, and then a fruit, so mango, papaya, and guava. And you probably have the situation like here listed. So now you want to change the value of one of the elements, namely the one with the index 2. The problem is normally you have to remove it and then change the value, and then you add it again, and removing frees the memory, and adding it again allocates memory again. And that's expensive, of course. So here we have a cheaper way. We can extract this node, this value from the container, and we get a handle which still reserves the memory for this data. Then we can, in this handle, we can change the key to 4, and then we can move this back into the container, and this all happens without any memory allocation or deallocation, which of course makes it cheaper to handle things. So this is not only to be able to change the key of a value in such a map, it's also possible to move, for example, a value cheaply from one map into another, or even into a multi-map. And yeah, that's supported now. Oh yeah, here's another example. We have a source value, a map of 1, 2, 3, and a destination value, and then we want to insert this new value into the destination map, which we extracted. And here we can, for example, we get the node handle to find out if it failed, what was wrong, what went wrong. I need some clarifying graphics here for this slide, probably. So, a few minutes left. Let's see. We still have some things. The first thing is a scoped lock. This is the third lock guard we have in C++. I apologize for that. We have lock guard, which is a simple guard. It's not the underlying mutex. It's just an object that uses a mutex so that the constructor locks and the destructor unlocks. And the first inter API was a lock guard, which could only lock in the constructor and unlock in the destructor. And then the second one was unique lock. Unique lock and lock guard came together with C++ 11. And the second one can more than just constructor and destruct a lock. They can, in the middle, they can do even during its lifetime unlock and lock when you need it in some places. It turned out that we made a mistake, or something unfortunate. And the point is, sometimes it's necessary to lock multiple mutexes. And if we do that, we have a function called lock. That's coming from C++ 11. This is not an object. This is not a constructor call. This is a function called lock. And it locks two mutexes with a deadlock avoidance mechanism. So it means instead of guaranteeing how the mutexes are locked, it finds out which is the right order to lock the mutexes to avoid a deadlock. Not in general. Your program can still have deadlocks, but not in this place. That's the point. And so the problem was we had to unlock both mutexes, and for that case, we had to adopt the locked mutexes by a lock guard. That was the interface we had to use. And this all became because the scoped lock, the trivial lock guard, was not variadic, so was not able to lock more than one mutex. And we fixed that. You might ask, why didn't we fix that in lock guard? The point would have been it would break binary compatibility. So it would mean that you have to recompile your whole program and your whole source code with using lock guards when switching to C++ 17. And that was not acceptable. So we introduced, too bad, but we introduced a new class, scope lock, which can take multiple mutexes. Here you see also how we work. We have compiler vendors there. We have people from every major platform, compilers, and also those who write libraries, and we discuss things like that very seriously. Binary compatibility is a good thing. Sometimes we don't support it if there are some workarounds, but for example, I can tell you that Visual C++ 17 is the first Visual C++ version, Visual C++ for Visual Studio 17, so the newest Visual Studio compiler, has a compiler number called 19.10 because it's binary compatible to the code from Visual Studio 15. This has never happened before. In the past switching from Visual Studio 13 to 15 was not binary compatible in any sense. So, but now they have it. So, and one reason is that compiler vendors fight for things like that, but you see, you pay the price. We have the problem of being backward compatible, a problem you all know. And we have the same problems like you. We have to support stuff we standardized 20 years ago, and we really would like to change things looking back. But that's the way it is. So a few other things. For atomics, we now have support to find out how to deal with your caching. I'm not an expert in that area, and how logs are used in the platform. So the first thing is, for any atomic data type, you can find out with C++ API whether it's log-free or not log-free implemented. So if you have an integer or your own data type, which is possible in C++, and use it as an atomic data type, you can find out whether the code generated will use logs, so create its own mutexes, or will be pretty cheap by the underlying CPU. And in the past, you had to use a C interface there, too bad, and now we have a C++ interface for that. And we have some portable information to deal with the cache line size of the level 1 data in your platforms. If you know what that means, you can probably explain it to me. I can't explain it to you what it in detail means. Some new mathematical features we have. We have adopted a whole sub-library for mathematical purposes, dealing with elliptic integrals, polynomials, Bessel functions, etc. And we have greatest common divisor and least common, what is M? I only know the German words for that. So, and we have a 3-argument hypotenusis for whatever purpose you need that. If you're a mathematician, you know that. And again, yet again, we have another API to convert integers to integral values and numeric values and the otherwise. We have had a lot of approaches. The most the approach which did cost the most was to use string streams, which is very, very expensive. So for that reasons, a lot of people still were using printf and scanf. Then the next approach in C++ 11 was to use toString on functions like s2ll, for example, to convert a string into a long. But they were still dealing with, for example, internationalization, so with locales, etc. So this was also pretty expensive if you didn't need localization. So now we have a low-level interface, locally independent, simple and fast, which just converts an integral number to a sequence of characters. You have to provide the buffer where this function writes in, and the other way around. And the interesting thing is, as a single side effect, we have the following. We can convert, we can guarantee round-trip ability for floating point numbers here, which is not a trivial case. Floating point numbers, to become round-trippable, these floating point numbers can have hundreds of digits if you write them out and then read them in portable. So that's now supported here with this API. So a low level, really something for usually library writers, but which really now finally replaces printf and scanf for the different formats like %f and %e. So I think that's it. We have a couple of bug fixes, of course. Maybe one interesting thing, const expr everywhere. Chrono, the library to deal with timers and time points and durations, is now a complete library of const expr except 1 or 3 calls. So every computation can happen, if needed, at compile time. The only thing that's not possible in compile time is to ask the operating system which time is it, and to convert to or from time t. Everything else can happen at compile time, which makes programming sometimes pretty fast. Okay, new type traits for those who deal with template code and do fundamental programming with template code. There are also new things provided. I think I don't go into details here now. And we also removed some things. We removed, for example, operator ++ for bool. Yes, this existed. When we introduced this in C++, people thought this is a cool idea. It turned out it's not a cool idea. And we removed the keyword register, so we no longer support it, but it's kept reserved for future use. So like auto, we might in future give register a new semantics. And we changed exception specifications, so the deprecated exception specifications without no except are no longer supported. But beware, there's one thing what we deprecate or remove in the library or in the standard in general. The other things is when compilers no longer support it. They usually care to be backward compatible even more than we in the standardization. And sometimes we do crazy things. For example, code convert, which is code conversion of strings and characters according to different code sets or character sets, was just introduced in C++11. It didn't work. Well, to be honest, we have nobody caring about it and knowing enough to do with it, so we removed it already. And we still are looking for people proposing a very useful thing, for example, to convert UTF-16 to UTF-32, which is very common in Java, but we have no API for that. And as I said before, it's your fault that it's not there, because you were not there proposing a corresponding library for the standard. And we temporarily discourage things. It's for memory reordering. It's very low level, where CPUs have guarantees when they can reorder statements in cache lines. We had a value there that really didn't work, so we really have something like temporarily discouraged. So for the moment, it should not be used. We come back later when we find out more details. So that's it. The highlights of C++ in general, even combined with the part 1 features, are a lot of new language features and libraries, and as a significant part, I list here everything, which is structured bindings, fold expressions, inline variables, compile time if, class template, argument deduction. And that's probably not complete. And you now saw the libraries and new libraries and helpers we got. And of course, each and everywhere we added cons expr wherever it is possible. So to be able to support the wish to move runtime computation to compile time computation. Just if you don't know where it's good for, this is used in the chrono library to compute with different ratios, which are the units, like seconds and milliseconds or so. And there we do compile time ratio computation to find out resulting units, which otherwise would have to be done at runtime and would cost time. What was not voted in C++? Modules. Modules, as a lot of people wait for modules, because this will solve the problem of large code bases taking a lot of time to compile. Because each and every time, with every translation unit, you again insert header files, even if you have precompiled headers, which go a little bit along this path. It takes a lot of time. And we are working on a new strategy to deal with that. I didn't want to say the word concept here, because concept is a concept we have in C++. So concept, which is a way to specify template APIs. Let's see what happens there. It's a long story what happened here. A lot of people are frustrated. A lot of people are not happy with what is currently provided. Anyway, there might, sooner or later, hopefully come something useful. Ranges is a library you can in beta test already. it's a solution of coming from the begin-end nightmare to something more useful and more modern. So when it comes in C++20, we will no longer pass begin and end of containers. We will pass the containers or sub-ranges of it. And we will have to deal with them like in Unix pipes, so where you can say, in parallel, we can compute that we take all the elements of one container, do one transformation, the other transformation, the other transformation, and then in parallel by multiple threads, the elements will be computed one after the other if that's possible. So we can pipeline computations and not using begin and end anymore. This will change C++ dramatically. Let's see whether it comes in C++20. Coroutines is in thread environments to define what shall happen under which circumstances when something is ready. The problem here is we have two different companies proposing APIs, Google and Microsoft, and they still fight. Hopefully there is something they can both think about and agree about in near future. And reflection you might know from Java, etc., so that we at runtime can find out what members, for example, a data type have, and then deal with that, so we could provide serialization, etc., like that. So that will be a big change, and a few minor things. So again, a summary here. I'm a little bit over time, 2 minutes, so it's time to finish. I think C++17 is a significant improvement. I now had 2 hours to explain, to show you what is coming. There is still the need to explain all the details, and there are a lot of details. We still find out what we standardize there to some extent. And we have the compiler support, so I would say this is a medium new version. It's a pretty helpful version, but not a revolution. And there will be books coming out, and one book I can announce here again is a book, the next edition of C++ templates, which was written 15 years ago, explaining all the details of C++ templates. And now we revised it after 3 years' work. We always postpone it because we had better things to do. But now it's almost done. It will be out in September. It will have 800 pages only explaining the template features of C++ 11, 14, and 17, and that's a lot. That's all. I'm here around only 1 hour. More than I have to go back and go to vacation. So I can't stay here. And so please contact me if you want here or just via email. And looking forward to see you somewhere else. And I thank you for attention and have a good conference. Thank you very much.